Hi students, now we are going to discuss the oscillations of a simple pendulum. So this is another example for the simple harmonic motion as well as the periodic motion. Now a simple pendulum is constructed by suspending a small mass which is called as the bob. The spherical mass is called the bob. It is attached to the free end of a string or thread whose other end is fixed, okay, in the vertical direction. The L is the length of the simple pendulum. You can see here on the top it is suspended at the point. That point is called as a point of suspension. And the center of gravity of this bob here, this is called the point of oscillation. So the distance between the point of suspension and the point of oscillation only is called the length of the pendulum. If m is the mass of the bob, then the weight of the bob is mg, which is acting in the vertically downward direction. Okay, this position now is called as the equilibrium position, or this is a mean position. Equilibrium position also is called as the mean position. And this one is called the extreme position, okay, right extreme. So extreme position is the position where up to which the bob will oscillate and it will stop for a while, and then it is going to return to its original equilibrium position. So the pendulum is going towards the extreme position and is coming back to the mean position. Then what will happen? It will overshoot. Okay, that full oscillation we are not going to discuss. So only it is a half oscillation I am going to discuss with you today. Now T is the tension in the string in the extreme position. Okay. Now you see here, I will take the initial position of the bob as A and here the extreme position of the bob as B. You can see two things here. One is A to B, the linear displacement is denoted by S. At the same time, the string or the thread is displaced through a small angle theta, where theta is called the angular displacement and S is called the linear displacement. Suppose if the bob is allowed to continue beyond the extreme position, its path would have been a circle, is it not? See here, from here up to this I have shown a part of a circle. So in this part of a circle, what should be the radius of the circle then equal to? That is equal to the length of the string L. Therefore, I can relate the linear displacement S is equal to radius L times the angular displacement. We have studied S is equal to R into theta, is it not? So I will write S equal to R into theta, which is also now equal to what? L into theta, L times theta. Okay, now I will differentiate this now with respect to time, ds by dt. Okay, that is equal to what? L into d theta by dt, where ds by dt is called the linear velocity and d theta by dt is called the angular velocity. If I differentiate once again, the second derivative will be what? D square s by dt square is now equal to L into d square theta divided by dt square. What is d square theta by dt square? It is called the angular acceleration, rate of change of angular velocity. Okay students, now this S is equal to L theta we have studied in the third chapter. Okay, then if you differentiate twice, the second derivative of the displacement on the left hand side will give you the linear acceleration, and the second derivative on the right side, keeping L as constant, it is L d square by dt square. So where d square theta by dt square will be the second derivative of angular displacement, and hence it is called as angular acceleration. So now I will write this as equation 1. Keep it in mind. This step will be used for the derivation further. Okay. Now you look at the displaced position, that is the extreme position. At the extreme position, what are all the forces acting on the system? Let us investigate. first force immediately due to its mass, that is equal to weight. So weight mg is always acting in any position, it is acting in the vertically downward direction only. See, here also it is vertically downward, at B also it is vertically downward. Then T is the tension, T is the force due to tension in the string. Okay, now I will produce this length of the string. Okay, I will extend this straight line so that this straight line makes an angle theta with the force mg. Okay, so I will resolve this mg into two components. One is along the length of the string. So this is the force along the length of the string. AS means along string. This force is acting along the string. And what must be its magnitude equal to? It must be equal to mg into cos of this angle theta, mg cos theta. So F AS must be equal to what? I will write here. F along string, okay? F along string is equal to mg into cos of theta. And the another component, perpendicular component, you see here. So this is F perpendicular to the string. PS means perpendicular to the string. So another force FPS, its magnitude must be equal to mg into sine of theta. So FAS is the force along the string and FPS is the force perpendicular to the string. Understand, children? And they are respectively mg cos theta and mg sin theta. This has to be understood very thoroughly. Hope you have understood these two. Now you see the diagram, children, and tell me which of these two components is acting towards the mean position. It is FPS, is it not? This force mg sin theta is only directed towards the mean position. So this must only be equal to the restoring force. Understand that? And the other force mg cos theta is opposite to that of the tension. So I will write tension, the force, resultant force along the length of the string, no? T minus FAS, T minus mg cos theta. This must be equal to the centripetal force mv square by r. Here radius is equal to the length, so mv square by L. So this equation, just for understanding we are writing, in no way it will be repeated in the derivation, okay? But you remember for solving numerical problems. So in the extreme position, the net force T minus FAS, that is mg cos theta, must be equal to the centripetal force mv square by L acting towards the center. I mean towards the point of suspension. Okay, now you tell me the other component FPS is equal to mg sin theta is acting towards the mean position. Is it not? That is equal to the restoring force. So the restoring force, the force which restores the pendulum back to the mean position is called the restoring force. So the restoring force is F equal to mg sin theta. It is equal to mg sin theta. But children, you see here, the displacement S is from A to B. Is it not? Pendulum is displaced from its mean position towards the extreme position. That is along the positive x direction. But mg sin theta is acting in which direction? Negative x direction. By the definition of simple harmonic motion, the restoring force and the displacement must be oppositely directed. Is it not? So I am going to write with the negative sign. Though it is mg sin theta, I am introducing a negative sign because this force is opposite to that of the direction of the displacement. So I am writing this is equal to minus mg, okay, sin theta. Okay, by the definition of SHM, this must be equal to what this must be equal to mass into acceleration of the system, is it not? So this must be equal to mass into acceleration. So minus mg sin theta is equal to m into d square s by dt square. The second derivative of the displacement is called as the acceleration. Okay, children? This is d square s by dt square is what? Linear acceleration. But now on the left hand side is the angular displacement, theta is involved. Either we have to convert theta in terms of a linear displacement or s in terms of the angular displacement. Now from the equation 1, what is d square s by dt square is also equal to, it is equal to what? L times d square theta by dt square. Is it not? So I am going to substitute here. So minus mg sine theta, okay, minus mg sine theta is equal to m into L into d square theta divided by dt square. Now m is getting cancelled. I will shift this L term to the left hand side. So g by L into sine theta is equal to d square theta by dt square. Okay, from the definition of simple pendulum, we have many times studied that the amplitude of oscillation should be very small. That means the angular displacement also should be very small, less than 10 degree. So when the angular displacement theta is very small, sine value of theta is nearly equal to theta. So I will write for small, okay, for small values of theta, sine theta is nearly equal to theta itself. So g by L into sine theta is now reduced to g by L theta. Understand? So I will write d square theta by dt square on the left hand side. So d square theta divided by dt square is now equal to minus, okay, here there is a minus sign, minus g by L into theta. This is the equation required for us. So I will number this as 2. So d square theta by dt square is equal to minus g by L into theta. Okay, children, the simple harmonic motion at the beginning of the chapter we have studied there are two types. One is linear SHM, where the force is proportional to the linear displacement, or the linear acceleration is proportional to the linear displacement. Whereas in angular SHM, the angular acceleration is proportional to what? The angular displacement. Is it not? Here in terms of angular acceleration we have written. Is it proportional to the angular displacement? Are we getting? This is the definition of angular SHM. So I am rewriting that from definition of angular SHM. Okay. So from definition of angular simple harmonic motion, d square theta by dt square, d square theta by dt square is now equal to minus omega square times theta. In the linear SHM, we had a habit of writing d square x by dt square is equal to minus omega square times x, where x is the linear displacement along the horizontal. Similarly, we wrote d square y by dt square is equal to minus omega square times y, where y is a vertical displacement along the y-axis. So this is angular SHM. So this is equation number 3. Now you compare the left hand sides of equations 2 and 3 are same. Therefore I am going to equate the right hand sides. So from equations 2 and 3, okay, I will write minus omega square into theta is equal to minus g by L, okay. So minus g by L into theta. Minus and theta get cancelled, so omega square. So this implies what? Omega square is equal to g by L. Therefore omega is equal to root of g by L. Omega is equal to square root of g by L. Now the period of oscillation, okay, period of oscillation of the simple pendulum is given by t is equal to 2 pi by omega. This is equal to 2 pi divided by square root of g by L is also equal to 2 pi root L by g. This is the equation which we have derived many times. In the beginning of this 11th standard, first chapter, dimensional analysis method also, we have derived the same equation. Do you remember or not? So T is equal to 2 pi into square root of L by G. So this is equation number 4. What next do you expect? Yes, we have to find the frequency of oscillation. Okay, so frequency of oscillation is the reciprocal of the time period. Okay, so I will write F is now equal to 1 by period, that is equal to what? 1 by 2 pi into square root of G by L. So this is the final equation number 5. So the same equation now we have already derived in the vertically loaded spring mass system also. Understand? Okay children, now the recapitulation is done very fast. A bob is suspended from a vertical point. Okay, so with the help of a string or thread of length L, and this position is called the mean position A, and here mg is its weight acting in the vertically downward direction. Then it is displaced to a new position B, so that its linear displacement is S, and the angular displacement at the point of suspension is theta. So we related S is equal to R theta, where R is the radius. But here the radius of the circular portion of a circle is what? The length of the string. So S is equal to L theta. And the second derivative d square S by dt square is equal to L times d square theta by dt square. This is to be understood. First you write this step. Okay, afterwards everything will be understood. Now at the extreme position B, you see that the weight is still acting in the vertically downward direction, mg, is it not? And if this angle is theta, you resolve this mg into two components. One component along the length of the string, that is FAS. AS means along the string, and the other one is perpendicular. Okay, that's vertical component. So FPS, PS means what? Perpendicular to the string. So along the string, the component of mg is mg cos theta, and perpendicular to the string, the component is mg sin theta. Then you will have to substitute, and finally you have to derive the expression T equal to 2 pi into square root of L by G, and the reciprocal of T, that is called F. F is equal to 1 by 2 pi into square root of G by L. I hope you must have understood well. Fine.